Hey, my name is Nick. I'm a software developer working at Gnosis, and today I'm going to try my very hardest to convince you that we should all embrace WebAssembly as a technology to help us decentralize our dApps even more. So to start off, what is WebAssembly? Well, WebAssembly is, to quote directly from webassembly.org website, WebAssembly is a binary instruction format for a stack-based virtual machine. So Wasm is designed as a portable compilation target for programming languages, enabling development on the web for client and server applications. So what does this mean exactly? Well, it means Wasm has these special properties. And the four ones that I think are most important are, first of all, that it's portable. So as the name implies, Wasm is an assembly language for a fictional virtual machine, kind of like EVM, if you think about it. This means that Wasm can run anywhere there is an implementation for this virtual machine. Its portability also stems from the fact that it is a compilation target, meaning that you don't actually write Wasm. You write code in a high-level language like C, assembly script, or C++, and that code gets compiled to Wasm. The second important property is that it's compact. So specifically, it has a very small binary representation. In fact, without much code golfing or anything like that, you can set up a hello world program with error checking in just 150 bytes. The third property that I think is important is that it is safe. So since Wasm targets a very minimal virtual machine, it's kind of like a glorified calculator. And so Wasm modules by default don't have any access to system resources at all. So additionally, there are certain design decisions in the spec, for example, around how memory regions are declared and how modules are actually validated for stack correctness before running that mitigate whole classes of security bugs. And lastly, it's fast. So if you leveraging approaches like just-in-time compilation, Wasm can run at close to native performance. And this is also partially enabled by the fact that the Wasm instruction set can very easily map almost one-to-one to actual hardware instructions. So in this regard, WebAssembly is very much designed for the web, and it shows in these properties. So portability, so it can run anywhere on computers to smartphones. You can probably even run it in a microcontroller, although I'm not sure why you would want to do that. Secondly, it has its small binary representation, is perfect for transferring over the web, especially in bandwidth-limited situations. And its safety makes it ideal for running untrusted code that you find on any website you visit, just like how JavaScript code in the browser is also sandboxed. And these same properties also make it very good for dApps. So portability means it's for everyone. It also has the benefit that code can run in the browser with traditional Web3 dApps, like JavaScript Web3 dApps, but also within Node.js, for Truffle projects, or directly in the terminal, as we'll see later. Its size efficiency makes it more easily distributed over decentralized networks or over IPFS. And its near-native speeds make it suitable for CPU-intensive tasks, like all the cryptography computations that need to be done, that otherwise and otherwise would be more difficult in things like JavaScript, which is much slower. So many dApps today are backed by additional services to help enhance the user experience and or drive on-chain protocols. So take Gnosis protocol, for example. This is a decentralized exchange that we developed at Gnosis, as the name implies. I'm sure many of you aren't familiar with it, so just to give a high-level description on how it works, limit orders are collected on-chain into batches. It's a batched exchange protocol. And at the end of each batch, off-chain actors, which we call solvers, compete to find the fairest possible settlement for these orders, which we call solutions, given the order book at the time for that batch. These solvers then submit these solutions on-chain, where they are evaluated by a smart contract, which determines which one is the fairest and awards a fee to the winner, and executing all the trades. So one of the big issues we encountered with this protocol is that submitting solutions became prohibitively expensive. Some of the design decisions were done at a time where gas prices were much lower. Yeah, so in this example, we here have a solution that cost around 170 US dollars to submit on chain because the gas prices were so high. These exorbitant gas prices made it so Gnosis run solvers had to simply ignore smaller orders. So this is because the fee mechanism works by collecting a small percentage on each trade. And this therefore means that orders had to be many thousands of US dollars for those collected fees to offset the gas prices and make it economically viable for the solvers to run. So that being said, Gnosis protocol is actually decentralized, and not only Gnosis run solvers are allowed to submit settlements and solutions. This means that users are actually allowed to compute these solutions and submit them on chain themselves. Now, the problem with that is that math is hard. In fact, handcrafting a solution is extremely difficult by hand. So someone like using something like Etherscan to just send a transaction with a manually computed solution to interact with GP and execute some trades is not really feasible for most users. This means effectively that users that do want to make small trades are just unable to on GP right now, even if they would be able to, even if they would be willing to pay the gas prices for submitting these solutions. So one other aspect of decentralization of Gnosis protocol is that most of the backend infrastructure is developed in open source. This means that there's nothing preventing users from running their own solver infrastructure to match their own orders. There are also guides on how to get everything set up and started, and a tech-savvy user could even configure one of these solvers to even prefer their orders, to protect their interests. Yeah. However, there's some pretty big caveats when it comes to the decentralization, this aspect of decentralization. The first being that the repository is hosted on GitHub and is owned by a Gnosis organization. And secondly, the Docker images that are used are hosted on Docker Hub and also under the Gnosis organization. While in the current day and age, this is fairly standard, but for the especially paranoid, this might not be decentralized enough. So Gnosis can delete the repository or rewrite the commit history for whatever reason. GitHub could take down the repository for whatever reason, far-fetched example being a DMCA claim or something crazy like that. Gnosis can retag images, potentially making it harder to recreate specific solver configurations, or Docker Hub can stop hosting the image, or rate limits users in it to a way that they can't use the image like they want to. It means that while the protocol in and of itself is completely decentralized, it relies on some core infrastructure pieces that aren't. Although in practice this isn't really an issue, there do exist technologies, like IPFS for hosting files, that can in theory be used to more resiliently host immutable code. Which brings me to Mesa. So this is the main front end for Gnosis protocol operated by the DXDAO, and it is entirely hosted on IPFS, so truly decentralized. One thing that is missing from the front end, however, is the ability to drive the protocol forward. In other words, it can't compute solutions and submit them. While this is theoretically possible to implement in JavaScript and run directly in the browser, the problem is that inputs are large enough and the problem is complex enough that performance starts becoming a limiting factor. So this is where Wasm can come to the rescue as a technology, taking advantage of its near-native speeds to turn any Mesa user into a solver. So this means users would effectively be mining for the Gnosis protocol and submitting solutions to drive the protocol forward. So I've been recently working towards a working Wasm solver using a graph-based price finding algorithm that we use in our price estimation service that could run entirely in the browser, thanks to Wasm. So what this means is the user would be able to get a suggested price for a trade they want to make, but also have a known solution for that trade that can be submitted and settled on Gnosis protocol. They would be able to execute the trades themselves by submitting the solution on chain, and this would allow users to continue using GP even if Gnosis, for whatever reason, decided to stop running their solvers. And not only that, if they are trading small amounts, they can decide that they are okay with paying whatever gas prices is there to make the trade themselves. And with this, the paranoid can rest a little easier, that they no longer need to rely on some centrally hosted infrastructure to make the protocol usable for them. Additionally, GP would be able to continue functioning even without any organization hosting services and be entirely driven in a decentralized way. So I want to move on to something a little bit different, which is another important piece and part of the Wasm ecosystem that, in my opinion, is criminally underused by dApps. So earlier I mentioned that it is actually possible to run Wasm CLI applications, and this is done through something called the WebAssembly System Interface, or WASI for short. And this standardizes an API for interacting with an actual system, such as allowing file system access, networking, etc., in a portable and secure way. So how WASI works on a very high level is that, well, to begin, Wasm on its own doesn't provide any of these APIs out of the box. So the host, so in other words, what is actually running the Wasm code, has to choose to provide functionality it wants the Wasm module to have access to. And WASI just standardizes sets of system interface functions, which allow a libc implementation to exist. It means that many existing C code bases or code bases in other programming languages with standard libraries that are based on libc, such as Rust, can simply just work with Wasm, as WASI does actually indeed provide a libc implementation, replacing the traditional syscalls that interact with the operating system with these WASI system interface calls. So for example, here we have some Rust code that calls print line to print a message to standard output. This gets translated by the compiler into a WASI system call, so WASI FD write in this case. And then the host provides an implementation for the system call. If it's a Linux host, for example, it would use a traditional syscall, write v syscall, for example, to write to standard out. But if this were run in the browser, it could just forward this call to console.log. So one caveat is that the libc functionality is not entirely, not all of libc is available this way. Most notably, things like threading, atomics are not currently possible, and this is partially because the Wasm itself doesn't support them fully, completely regardless of what WASI does. But this hasn't stopped some high-profile large projects from compiling and working in Wasm, such as Nginx or Nginx. I'm not really sure how to pronounce it. The famous HTTP server. Now, one rightfully might be concerned with security of this. If a Wasm application could just access host file system with the WASI interface, then what's the point? Well, it turns out that WASI standard did think of this. Under the hood, because a Wasm application doesn't directly interact with the host system and goes through this indirection through the WASI interface, the host system can arbitrarily decide whether or not the Wasm application should have access and has sufficient permissions to perform a given operation. This is completely outside of file system permissions at an operating system level. This is the runtime that decides. So in preparing for this presentation, I actually decided to do a little experiment just to validate and make sure that a WASI application indeed is secure. For those who are curious, I used a runtime called WasmTime, but it's not super important for this. So consider the following pseudocode application, where I just read an SSH key. So knowing that WASI is very security conscious, I fully expected this to fail, but I was actually very pleasantly surprised how. My initial instinct was to expect the file would just not open because the permissions were not explicitly given at runtime for this application to read your SSH key. However, it actually failed even before that. It failed in getting the value for the home environment variable. So this makes perfect sense, especially since it's not uncommon to store sensitive information environment variables such as API keys and such that could be compromised. This is a big step up from just providing a compiled binary or JavaScript to run with Node.js on your system. It's for users to run their own infrastructure, where the users would be required to do sandboxing themselves, either with a virtual machine or with Docker, or they would risk malicious applications from compromising their private information. So speaking of Docker, Docker actually offers many of the same security guarantees as Wasm WASI. being able to run applications in a sandbox environment and not expose secrets from the host, without actually having to resort to more harder hitting solutions such as a virtual machine or dedicated hardware. It does have a few downsides, a few big downsides, in my opinion, compared to Wasm, in the context of decentralization, at least. First of all, it's hard to host images in a decentralized way. Like, you can't trivially host the Docker image over IPFS, for example. This is not for Wasm and Wasm-Wazi. These applications are single.wasm files, and they can easily be added and shared over IPFS, for example. And Docker is not as portable. So if you have an x86-64 image, then you need an x86-64 Linux kernel to run the x86-64 container. And Wasm is completely operating system and architecture independent, and just requires a WASI-enabled runtime to work. However, there still are some missing pieces, and there's still a way to go. So for this presentation, I also tried very hard to compile an Ethereum client that runs on Wasm-Wazi to see if it was possible. And unfortunately, it isn't. So my first attempt was with Open Ethereum, seeing as Rust has fully embraced WASI and they have really good support for it. But unfortunately, Open Ethereum relies on some system APIs that haven't made into the WASI standard, such as some async socket features that it uses. Also, in Geth, the second one I tried, unfortunately, Go just can't compile, doesn't have WASI support yet, so it was just not possible. All right, so what do we do now? So one thing that we can do moving forward is to standardize a Wasm Ethereum interface, much like how there's a standardized Wasm system interface, except for Ethereum. This would allow Wasm modules to have a standardized way of interacting with an EVM on behalf of the user and have some standardized functionality that they have access to. So this would be conceptually very similar to what MetaMask does in dApps today, where it injects a Web3 API and that your JavaScript has access to in the browser. In the case for a standardized Wasm Ethereum interface, this Web3 API would be injected into the Wasm module. And just like with MetaMask, this would allow the Wasm module to sign and send a transaction on your behalf, but without ever actually having access to your private keys. So I whipped up a very quick example of what something like this would look like. So I have a little CLI application that downloads a Wasm module over IPFS. Then the Wasm application calls the host to ask for it to sign a transaction. And the host, the private key is being kept in the operating system keyring, which is used to sign the transaction. And so just like with MetaMask, this application never actually has direct access to the private key. And in theory, you could integrate hardware wallets, and this would be done without any modification to the dApp itself. Just the runtime would have to support it. And furthermore, the configuration for which node to use and which Ethereum node or IPFS node to use is done by the runtime, which means that you can choose one that you trust, and you're not required to use whichever one is configured by the dApp itself. Kind of like how MetaMask does it. Yeah, and you can even come up with a standardized Ethereum interface that could run both in a browser environment alongside traditional Web3 dApps, but also one that runs on the console. So truly run everywhere. So I really hope that I convinced you guys that we should use more Wasm everywhere, and that it's super well suited as a technology for truly decentralized apps. So we should start hosting Wasm on IPFS, using Wasm in the browser for performance critical code, and also providing Wasm applications so users can run their own infrastructure in a sandbox environment and not have to worry about their SSH keys being stolen. So all the code for my experiments and stuff, they're all available on GitHub along with the slides and the notes. And yes, it's on GitHub. The irony is not lost on me. Just please don't judge my code. It's very rough and was done purely for this presentation. Thank you very much for listening. I appreciate your time. Yeah, that's it. is there time for questions? Does it work that way? I'm not entirely sure.
Yeah, I guess if people are still interested in, I mean, it's up to them. I mean, this is not a physical room, so we're not taking up anyone's space.
I thought that maybe like the session closes or something.
Yeah, maybe they really wanted to simulate a real conference, but no, people can stay. You can stay as long as you want.